Hi, everybody. I'm Mike Fitzgerald. I'm the external co-lead of the workshop. I'm an associate professor at UCLA. Work in infrared instrumentation and high contrast imaging. And I'm here to introduce the next topic. Our next topic actually has two different talks on it. And this has to do with the technology that goes behind all of this great science. And this, as Carl went over the history, there's been a lot of technology development along the way that has enabled these great discoveries. And this topic is so big that we've split it up into two different areas, focusing on space and the ground. And so I'll introduce our first speaker, Dr. Eric Cady. Eric is an engineer at NASA JPL, and he specializes in high contrast imaging instrumentation. He actually got his bachelor's degree here from Caltech, like myself, and then came out of the Princeton group in mechanical and aerospace engineering, the Kasdan group, where he got his PhD in 2010. His work really covers a lot of the broad swath of technology that goes into these discoveries. He works on chronographs, star shades, how to do the wavefront control, the systems behind that, optical design and modeling of those things, hardware assembly, integration, software, automation, and operations both in the lab and the observatory environment. And so we're going to have these, Dr. Cady, and then I'll introduce Dr. Jared Males after his talk, and then we'll do Q&A at the end of the two talks. So, Eric.
Thank you. Thank you, Mike. Just coming across all right? Okay. All right, so as Mike said, I'm Eric, and I'm going to talk to you guys about doing high contrast imaging and the technology to do that from space. It's not entirely separate from ground, but it does make a nice way to split up the sort of things we're talking about. So I'm going to do, because doing things in space is not generally easier, but they can be easier to talk about how things happen. I'm going to cover a little bit of the real one-on-one stuff. What is a coronagraph? How do we find these things? What have we done to date so far? And then I'll talk a little bit about where the technology is going. The term starshade came up briefly. I'll talk a little bit about what those are, and I'll talk about where the technology is going to be going in the future. So Carl came and gave you guys, what are we doing, why are we doing it? I'm going to focus on how are we doing it. And to start with, we'll talk about diffraction. Diffraction is how light moves through optical systems. It has lots of fun effects, but the key one that's applicable to coronagraphy, and I want you to focus on this one today, that when you take a picture of a star, you're never taking a picture of a single little point. When light is focused down in a telescope, we always like to draw it with these nice little rays, and they're all meeting at a nice little point. It doesn't actually happen like this. The shape that it actually makes is dependent on what shape your telescope is. If you were to have a nice circular telescope, and you heard some discussion of elliptical apertures, the reason you would do those is so you end up with something that looks nice and circular. You end up getting what's called an Airy pattern. It's these little series of circular rings. This image is called a point spread function, or PSF, and you'll see PSFs appear quite a bit in subsequent slides. So you're getting this nice little core where most of the starlight is, but you also have these wings, these structures that are sort of fading out as you get farther out. And these wings are the challenge. If all the starlight fell right in that core and stopped, no problem. We can see a planet right here. But these wings are, unfortunately, also in the same place where we want to look for interesting structures. And I'll just jump out and say this is not all a little theoretical exercise. This, in terms of coronagraphy, I mentioned this guy's called the Airy pattern. This is a picture taken with the well-corrected sub-aperture in Palomar. What that was is the Palomar telescope. They picked off a little section of it, which was big and from one side of it, about as big as they could get, and it was circular. And when you image that guy, you get something that looks sort of like this guy. You have this circularly symmetric PSF going on. And I said that this was related to the shape of the aperture. If we were to move over to something like Hubble, which is not just a big circle, it's got a secondary obstruction, it's got spiders, it's got some side features. You end up with something. It's got some different circular structure, some asymmetry, and it's got these diffraction spikes coming out on the sides. And this is sort of pointing towards a general feature that you see in these apertures is the more stuff you have going on, particularly these thinner features, they tend to scatter light out more widely. This is again not an entirely academic exercise. If we were to take this guy and we were to zoom out, so now you're seeing this guy right at the center, you're seeing these long spikes. These are things you actually see. This is a picture of 30 Doradus taken with a wide field camera 3, and you do in fact see these diffraction spikes sticking out of these stars. So this is not something we're just modeling. This is what actually happens as we're propagating light through these telescopes, and this becomes a real thing to deal with. As I said, we're looking for things that are, they're very faint, they're very close to that center, and they sit right under the wings. If we were to take a slice through this guy, you can see all these rings, and you can see that planet, or you really can't see that planet, because this guy's on a log scale. Every time you drop one of these down, you're down by a factor of 10. So this guy is really, really faint. And so the real challenge of high contrast imaging, space or ground, is to get rid of this diffracted starlight, to suppress these wings, to see these planets that are really nearby and faint. And I'll just reiterate this point. As the PSF depends on the aperture you're using, different telescopes may need different solutions to get rid of this diffracted starlight. There is not one all-purpose solution for everybody. So the one method to doing this, probably the biggest one to date, is the coronagraph. You've heard the term get tossed around a couple times. It's sort of a general class of instruments, and these use the diffraction to cancel the starlight inside the telescope. So it's a single instrument. They're designed to be minimally affected by the planet light. And the reason they have the name coronagraph is they first showed up in the 1930s to look at the solar corona. Prior to being invented, if you wanted to look at the solar corona, you went out and chased eclipses and looked at it for a couple minutes at a time. And it turns out that if you build something like this, where you're basically putting a big old disk over the sun, you can watch it continuously. This is actually it's quite interesting. It's a film. This is a still from a film made in 1935 of one of these solar prominences, and you can see the edge of the disk that was used to block out the sun. And I'm showing this. This is kind of an old drawing, and maybe the notation's a little obscure, but this is a diagram of one of Bernard Leo's first coronagraphs for the sun, and it's got all the key features of what we'll call the Leo coronagraph. You have a big old mask here that the sunlight is focused onto, and then you have the second thing, which has become known as a Leo stop, where all the diffraction that comes from the edges of that big old disk you stuck in there gets blocked out by this sort of undersized shape. And this sort of general coronagraphic architecture leads to what we call the classical Leo coronagraph. It's got the focal plane mask, that big disk I'm talking about, which is you just slap that in front of your star, and it takes out a bunch of your starlight. And that's good, you gain some dynamic range. You can expose for longer without saturating your camera. But by itself, that's not necessarily enough. And what we do is we introduce a second piece of hardware called a Leo stop, that when light propagates past this mask, it tends to leave a lot of diffracted light around the edge near where that pupil was. And if we put an undersized pupil shape and we block out that ring, suddenly that bright star becomes a lot fainter. Not just at the center, in the wings as well. And that's the key point. It's not just suppressing the core that doesn't do much for you. It's suppressing the wings that's the key to doing a successful high contrast imaging. And I should point out that this is not theoretical. This is pretty much, I think, covers the state of space coronagraphy today. There's been 3 of these classical type LEO coronagraphs in various instruments. There's actually been, I think, 4 or 5, but only 3 of them have actually been used for this purpose. NICMOS, the HRC and ACS, and STIS have been used to take pictures of various planets. I'll say that the Fomalhaut planets, which Carl talked about previously, have been pretty much the best for taking pictures of, and things like HR 8799b, you've taken a very call it an ugly picture, something like this guy, and then you do a lot of processing on the data afterwards, post-processing. It's usually referred to pull that planet out, and it's actually, we've been able to see the entire system from Hubble. That was the picture right at the beginning was showing the B, C, and D planets. And these, they have the features I talked about. They have your masks, they have your LEO stops. NICMOS is actually interesting in that these guys are using little stops that you pass through. NICMOS, on the other hand, has a mirror, and it cut a hole in the mirror, and it's picking off the starlight that way, which is equally valid, it turns out. So this is sort of where we are now. We can see it. We can directly image a few planets, but I've got at least 15 minutes left to talk, so I got to say something. It turns out there's a couple little details that are a bit of an issue here. So I blew up the last image from that classical LEO slide and cut a slice through it, and there's 3 things I want you to take away from this. The first is that using the mask plus the LEO stop suppressed the wings. It's not just that we blocked out the center bit. Over on the side here, there's a lot less starlight, even though we didn't put a mask right in front of it. That ability to suppress the wings is one of the key reasons why a coronagraph is very useful. The second, and this is something important to think about when we're talking about different types of coronagraphs, is that the planet, you can see this was the star, and this was the planet, the little dashed lines. The planet is slightly affected as well. A little bit of the planet light has been cut out. So we do need to be careful about this. We do need to, in considering what coronagraph is appropriate for a system, we do need to think about things that are not suppressing the planet as well. Because if a coronagraph will do that. If the planet was in so close that it was behind that big disk, it's gone. And the point where it sort of cuts off about 50%, where we traditionally call that the inner working angle. And that's about as far in, more or less, as you can work with any particular given coronagraph. The last point, and the most important, is even given all that optical hardware and work, the planet is still too faint to see. Here's your wings, and 4 orders of magnitude down, you've still got your planet. So just sticking with the classical LEO coronagraph is not enough for the kind of planets that we want to be able to image here, the faint close-in ones. And it gets worse. So that model I showed was with a perfect system. If you were to introduce small optical imperfection in this system, in this case, John Christ kindly provided me with the optical aberrations associated with Hubble. It takes that sort of nice round thing and just scrambles it, so that when you cut it through, not only did it go from something that we kind of understood to being all over the place, also your wings are back up. You just threw a lot of light back out there. So these speckles are going to be a problem for us as well. Even if we make a very well designed coronagraph, we need to be able to deal with these speckles. So how do we do with this? There's two things we do. First of all is we've gone to better designs, and a lot of people have gone to better designs. I'm sorry, I apologize in advance if I didn't put your favorite coronagraph up here, because there's at least a half a dozen other types. But these sort of cover the main categories of things we can do. Is we can change the pupil we're using. Instead of thinking of a circular pupil or something like Hubble, we can make it into the shape that we want it to be. We can make it kind of a smooth and grayscale. We can make it into a little bit. This guy's a little bit more blobby, but the idea is that when you focus this guy down, instead of getting those concentric circles, get something that's specifically designed with very dark areas. You can, instead of changing the amplitude of the light, you can change the phase. That's what this guy does. Is it when this guy's focused down, it just creates a big half-plane region where there's very little starlight. So you can deal with the pupil. You can deal with the focal plane instead of putting a big black circular mask that blocks things out. You can change the phase or the amplitude of the light. So you can interfere part of it with itself. You can block some of it and interfere some of it. That's, for example, what the hybrid Leo does. Lets a little bit of starlight through to interfere with itself, and then introduces some additional phase so that the light will interfere with itself downstream. We can also think about introducing additional optics, and I'll toss out the Pia coronagraph, which maybe you can see it uses a pair of highly aspheric mirrors, though I guess more modern designs are less highly aspheric, and you can see that they're distorting, that these reflections are kind of going all over the place. They're basically remapping the light going through the system to let you look at things that are very close. And as a bonus, they let a lot of light through. And so, I said there's 7 coronagraphs here, and I said there's half a dozen others. Why do we care? How do we distinguish between the two? It turns out to be a lot of factors in play. How close can you get your inner working angle? How much light do you let through the system? You can say what wavelengths does it work at? Some of these are very effective over larger band passes at once. Some of them only work smaller. So these are the sort of things you can play against each other in deciding what chronograph to use for a situation. The other thing we can talk about is wavefront control. This is to deal with those speckles. What we want to do is measure the aberrations, what's going on with your optical surfaces that's causing these speckles to appear, and we can cancel them. And we use mirrors to do this that are actuated. There's a couple different ways to do it. I've got 2 of them on the side. This guy over here is a little MEMS guy. This one uses a series of actuators that more, I guess, macroscopic actuators that are physically pushing, pulling on the face sheet. So you can put these into your system, and if you've carefully measured what was causing those speckles, you can then at various steps cancel them out and get what we're calling a dark hole. It's a limited region around the star where we very highly suppress those wings, and those are the areas that we can look for planets, even in the limitations of a realistic system. The other alternative to doing wavefront control, and Carl alluded to this briefly, is what we call a star shade. It's instead of letting the lights enter the telescope and get all aberrated, we block the light before it enters the telescope. Occasionally called an external coronagraph. And if you've chosen the size of it right, it doesn't block the planet, but it blocks the star. No wavefront control needed. And this is a diagram taken from the EXO-S mission report, which was a companion to the EXO-C, looking at a starshade probe scale mission. And this is extremely not to scale. The actual separation between a telescope and a starshade is on the order of tens of thousands of kilometers, which introduces its own problems, as that's larger than the size of the Earth. So, as with chronographs, starshades were developed to look at the sun as well. In this case, they were developed they first tried in the late 40s as basically the disk on a stick, where you're sticking that in front because the problem is same thing. You have the same issues with solar observations as you do with exoplanet observations. You've got that starlight that's entering and going all over the place, and it turns out, as particularly with something as bright as the sun, if you can get that light out before it enters your instrument, saves you a lot of trouble. And right now, for example, there are a couple of these types of instrument right now on the SOHO observatory. The C2 and C3 chronographs on LASCO are looking at the sun. This is I pulled this off a few days ago from their live feed. They actually you can go on right now and see what's going on with the sun. So they've got two of those, as well as one internal chronograph. They're doing solar observations. The starshade, in contrast to this is all done within the observatory. The starshade would be flown externally. As I said, tens of thousands of kilometers. The starshade itself is tens of meters across. Usual numbers, call it about 30 meters, is probably a good number. And what it does is, at that extended distance, it creates a very, very deep shadow. And you put your telescope right in that center there and fly the two of them in formation with the telescope pointing at the star and the starshade in between. And you've shaped your edge to deal with diffraction, because even when you're talking about these separated spacecraft, you still have diffraction to deal with. I'll say, I've talked about these before, and people have said, "Oh, that's great. When's it flying?" Well, it's not. It's still a concept. It's actively under development at several places, JPL being one of them. It's promising. We're still looking at it. It's got trade-offs with the coronagraph. So going into the future, we've got JWST, and I know Carl talked about this at length, so I won't talk about it at that much length. It does have a couple of coronagraphs in it. The MIRI instrument has some 4-quadrant phase masks. There was a picture of those in previously. Those are, you put your star right in the center there, and these two sides change the phase of the starlight, so it tends to cancel with itself. And then you've got a plain old traditional LEO mask. NIRCam is something a little different. It's got what's called a band-limited LEO mask, where instead of having a dot, these guys are forming a sync square profile. And the idea is that the light that shows up at the LEO stop downstream, instead of being that sort of broad structured shape that covered the whole aperture, it's much more contained to those edges, so it's much more easily blocked by a LEO stop. So this is sort of a second generation type of LEO coronagraph. And I'll jump last to W first, and I have a fondness for this one because I've spent quite a bit of my time the last couple of years working on this. This is a dark energy mission, but for purposes of imaging, we want to think about the dedicated coronagraph instrument, which is sort of the secondary payload for W first. And it has 2 coronagraphs in one. And you can switch between them by switching filter wheels. They have different focal plane masks and LEO stops and different pupils. And they're designed for different purposes, tuned more or less to their strengths. Hybrid LEO is doing imaging. It's got it can see more, have a larger dark hole at the same time, and so you can look for planets more effectively. The shape pupil can look in smaller regions. In these little wedges, if you can see down here. But the advantage to that, it can look over a broader band. And so those guys are going to be used with an integral field spectrograph to do spectroscopy of planets, and the hybrid LEO is going to be used to find those planets. So that is the immediate coronagraphic plan, and other possibilities, HabEx, LUVOIR, maybe, possibly a star shape with W first, or maybe one of the other two, also a possibility. There's still things we're looking at. And there is, of course, plenty of imaging to be done on the ground, and at that point, I will toss this over to Jared, who will tell you about imaging to be done from the ground.
All right, thank you, Eric. Our next speaker on the topic is Dr. Jared Males. Jared just finished a Sagan Fellowship at the Stewart Observatory at the University of Arizona, and he's now begun as an assistant astronomer, so congratulations there. Jared works on adaptive optics systems and extrasolar planets. He's been a big part of the Magellan AO project and is now leading the development of MAG-AO-X, which is a new extreme adaptive optics system for looking at exoplanets primarily in the visible wavelengths from the ground. I'll turn it over to Jared for learning about ground-based technology.
Okay, thank you very much. So Eric gave a great introduction to the coronagraphy and wavefront control that we have to do to detect exoplanets. And as I'm going to hint at, we have all of those problems on the ground too, but we also have a much bigger problem we have to deal with first. And so telescope diameter is kind of the big reason you want to stay on the ground. And as Carl introduced very well, there are two big advantages to having a large telescope. You get more photons because of pi d squared, and you get better resolution. So this is the area pattern that Eric was showing. And then the full width at half max, what we typically think of as the resolution limit of a telescope, goes as 1/d. So the bigger d is, the sharper the image is. And so you get to see fainter things closer to the bright stars if you have a bigger telescope. And as a rule of thumb, I don't think this is controversial, it's always easier to build a bigger telescope on the ground than it is to launch it into space. And we have a lot of proof of that. So we've been building big telescopes for decades now. So these are just some examples of telescopes that are currently involved in high contrast imaging of exoplanets. There's the Magellan Clay telescope. So remember the JWST telescope that Carl and Eric were talking about is 6.5 meters. We've had that on the ground for almost 20 years now. And we have the Subaru telescope, 8 meters, Gemini South, and there's also Gemini North, 8 meters. The European VLT is 4 8-meter telescopes. There's 2 10-meter Keck telescopes on Mauna Kea, and there's the LBT on Mount Graham in Arizona, which is 2 8 meters that actually, because they're mounted together, you can actually think of those as a 22-meter telescope. And we're already building the future. So we're going all from 25 to 39-meter telescopes are under construction. You can come to Tucson and see 4/7 of this primary mirror already cast. And the TMT and ELT, they're in various stages of construction as well. Ground is being broken, mountains are being flattened. So we're doing this. We're making very large telescopes on the ground. But there's a catch with all this. We have the Earth's atmosphere to deal with. And because in the Earth's atmosphere, even on the clearest, darkest night when you're looking at a star, there's temperature variations in the atmosphere between the telescope and the starlight, which causes index of refraction variations, which corrupts the wavefront coming in. And this is why stars twinkle, is because of this turbulence blowing between you and the star. And a key thing is the characteristic scale of these index of refraction variations, what we call R0, that should be a subscript 0, is typically much less than the diameter, much smaller than the diameter of the telescope. And so this is familiar after Eric's talk. So if this is a pupil, the primary mirror of the telescope, and you have a perfectly flat wavefront entering that telescope, like you would if you were in space, you get this airy pattern. But on the ground, our wavefront actually looks something like this. So this is sort of a typical Kolmogorov turbulence phase screen. So that's Kolmogorov is the model of turbulence that we typically use. And over here, you see what happens to the airy pattern. And just so that you can recognize it as an airy pattern, I've actually made this a fairly weak turbulence, so you can think of this as being at long wavelengths. At shorter wavelengths, this is much worse. And I'll just bounce back and forth so you can see how bad that is. So remember, we're trying to find planets right in here. And now we've made all of these speckles that are blocking our light. And this affects everything. So the coronagraphs that Eric was talking about now don't work as well. It makes the problem much harder. But we have a solution called adaptive optics. So over here on the right, this is a very nice cartoon block diagram of an adaptive optics system. So just stepping through this, you have light coming into the telescope, and the wavefront has been distorted by this turbulent phase screen in the atmosphere. And it comes in and it hits this deformable mirror. So this is the same deformable mirror technology that Eric was talking about with wavefront control. We use for adaptive optics on the ground. And you can see this mirror takes a shape that should exactly cancel the aberrations coming in from the atmosphere. After it bounces off this mirror, it hits this beam splitter. And we send some of the light to a science camera, which I'll talk about a little more in the next couple slides. And some of the light goes to a wavefront sensor. And the wavefront sensor's job is to actually measure this turbulence, actually measure the shape of the wavefront. And then you have this block diagram control system. You could just write computer. So its job is to measure this wavefront, decide what shape to put on the mirror, apply that, and then do this thousands of times a second. And so this is a closed-loop control system that typically runs at least 1 kilohertz. I think the record right now is 3.5 kilohertz at SCEX-AO. And so what happens is on the other side of this beam splitter, the science light going into our science camera is now these nice flat wavefronts. And as I said, these key components are the deformable mirror, the wavefront sensor, and the real-time control system. And the limit on how flat these wavefronts are is how fast you can run this. So I said that we can at least get to 3.5 kilohertz now. The number of actuators, so how many times you can bend this mirror, and how bright the star is. So you have to have so much starlight hitting the wavefront sensor so that you can actually take this measurement. So here's that same cartoon diagram of an AO system. And over here is a schematic of a real exoplanet imaging AO system. This is the Gemini Planet Imager. And so just to orient you, so this block diagram of the sort of workhorse AO system actually is just this part of this diagram. So you see here, in GPI, the DM is actually 2 different DMs. And here's the wavefront sensor right here. And there's the beam splitter that splits off that light into the wavefront sensor. Not shown on here is GPI's control system. And then what in this block diagram is just this one little box is actually all of this stuff. And you'll recognize some of this stuff from Eric's talk. So there's the coronagraph. So this is an apodized pupil Leo coronagraph. I'm pointing here, I'm calling this whole thing a low-order wavefront sensor. It's a little more complicated than that in this case. But this is that post-coronagraph wavefront control that Eric was discussing. This instrument is basically responsible for doing that. And then you have the actual scientific measurement apparatus. Here it's an integral field spectrograph, which has a lenslet array. It breaks the image up and takes a bunch of different spectra. And that's how those spectra that Carl showed are produced, is inside that instrument there at the end. And this is a block diagram of the SCEX-AO, the Subaru Coronagraphic Extreme AO System, PI Olivier Guillon. And this is kind of showing the same thing as GPI. It's definitely a different design. But here I wanted to highlight all of the different control loops. So this, dealing with high contrast imaging, especially on the ground with AO, is really a control problem as much as it is an optics problem. So you have the Subaru 8-meter telescope, and it comes in and it first goes through a facility AO system, and then it enters the SCEX-AO Extreme AO system, which is this 2,000 actuator deformable mirror. And here's that main AO loop. This is the wavefront sensor feeding, getting signals from the DM and feeding back the control signal at 3.5 kilohertz. And this is happening with visible light in this case. And the science light goes over here to the coronagraph system. And this is just like Eric was talking about. This is, and in this case, it's selectable set of coronagraphs depending on what kind of science you're doing. And then it feeds a number of focal plane instruments. So light rejected from the coronagraph itself gets used by this near-infrared camera. And so there's another control loop here that is cleaning up that light right at the focal plane after it's been rejected by the coronagraph. There's an instrument coming online called MKIDS. This is an energy-resolving infrared detector that itself will measure speckles and feed back information to the AO loop. So you have another loop running here. And then there's the Keras spectrograph, which is in the process of being commissioned, which is what will actually take spectra of exoplanets and itself will provide information about speckles and speckle evolution. So there are a number of systems similar to GPI and SkexAO on Sky today already taking exoplanet images. So there's the MAG-AO system, which I spend a lot of my time working on. We work from the visible to 5 microns. There's LBTI, which is on that 22-meter baseline large binocular telescope. Project 1640 at Palomar. GPI, which I've mentioned. There's SPHERE, which is the European instrument on the VLT. It's an extreme AO imager dedicated to exoplanets. And SkexAO working at Subaru. So I'm just going to go through some examples of these, of 3 of these instruments and some of the science products. And Carl's already given us a very good introduction to the science we're doing with these instruments. So this is the Magellan AO and the LBTI AO systems. They're actually, Magellan AO down here in Chile is really a clone of the 2 AO systems that feed those dual mirrors on the LBT. We use adaptive secondary mirrors. So this is basically a 1 meter diameter, but only 1.5 millimeter thick glass shell with magnets glued on the back. And we push and pull on those magnets to deform the mirror. This shell is so delicate that, if you picked it up by the edges, it would just crack down the middle. So it's a very, very delicate and sensitive optical instrument. The nice thing about these adaptive secondaries is they're very good for working in the thermal infrared because you have to have a secondary mirror to begin with. And so by replacing the secondary with our deformable element, we don't have to add additional optical elements to have an AO system. And up here you see an example of what having that thermal infrared capability can do. And so in this is a multicolor image. In the red and green light, you're seeing L-band and K-band infrared light from the LBT. This was taken with non-redundant masking, which is a technique for getting even higher resolution, of this planetary system called Lick Calcium-15, which Carl mentioned before. And what's nice about this image is you see that infrared light, the red and green light, of 2 planets plus maybe a 3rd planet. And that was taken with the LBT. And nearly simultaneously with the Magellan AO system down in Chile, we were observing this system in H alpha. So this is at 656 nanometers. This is the emission line of excited hydrogen. And as Carl said, this is a signature of accretion. So we see with MAG-AO, at the same time as these infrared observations, we were seeing this planet still accreting hydrogen. So this is a baby planet still forming around Lick Calcium-15. I mentioned the SPHERE instrument. This is on the 8-meter VLT, also in Chile. And I'm not going to go through this diagram in detail because though it's a different design and has many different capabilities, you will recognize many of the same components that I showed you from GPI and from SkexAO. And as you can see, it's not small. There it is bolted to the 8-meter telescope. And I mentioned GPI, the Gemini Planet Imager, which is on Gemini South. And Carl was talking about 51 Area B. And so that's an example of the kind of science that these extreme AO systems are doing right now. And we have just started a new project to build a new extreme AO system at Magellan called MAG-AO-X. It's the extreme version of Magellan AO. And this is largely similar to SkexAO in that we're going to use a 2000 actuator DM. We're going to try to run as fast as we can. But our our goal with MAG-AOX is to push into the visible and to be able to do 1 lambda over d, so get the finest resolution we can on a 6.5 meter telescope, and do coronagraphy at that inner working angle in the visible. And so what I'm showing over here on the right are simulated PSFs produced by our AO system without a coronagraph and with a coronagraph in H alpha. So this is invisible light. This would be going after those accreting protoplanets, trying to observe planet formation in progress. And as you can see with the advent of these fast, low noise, extreme AO system, even on a 10th magnitude star in good seeing, so at Las Campanas, 25th percentile seeing is half an arc second. We're able to take very nice images and even get down to 10 to the minus 4 raw contrast behind our coronagraph. And we're very excited. We've just been told that we've been recommended for funding at the NSF, and so we're entering our preliminary design phase. And you can see this is our conceptual design here of what that instrument's going to look like. So as I was saying just a minute ago, we've reached this point where we have these extremely fast deformable mirrors. We have low, almost zero noise, fast detectors from the visible through the infrared. We have these fantastic energy resolving detectors called MKIDs. So for AO systems on the ground, we are no longer really limited by technology. We essentially can run as fast as we need to, and we don't have to worry about noise. And so we're reaching this point where we're limited by photon noise. And it's photon noise on our wavefront sensors. So we can only measure turbulence so well because stars are only so bright. And that means that we can only have so many degrees of freedom in our system. We can only chop up the light into so many pieces before we run out of photons. That also limits our system speed. Because stars are only so bright, we can only run the AO system so fast before we, and then we're always behind the wind because of photon noise. And this puts an overall limit on image quality that we can achieve from the ground. And the key metric that we've been talking about is contrast, and this is the ratio of detectable planet brightness to star brightness. This is what Eric was showing. So before I go on to my last few slides, I want to just put out a caveat here that space people and ground people use contrast in different ways. So this isn't universal, and we all work together, so we kind of know how to talk to each other. But in case you're listening to a talk by someone who works primarily in space, or you're listening to a talk by someone who works primarily on the ground, they often mean different things. So a space person often talks about raw post-coronagraph and wavefront control contrast. So this is just what that ratio of PSFs that Eric was showing looks like. But on the ground, we usually mean our final contrast after we've done all of our post-processing, after we've done hours of integration. Sometimes it's months and years of post-processing work goes into this. But the problem is, what that means is when you have a space person and a ground person talking together, the space person usually thinks the ground person is crazy because they don't understand why they're getting the contrast that they claim. So keep that in mind when I show you these next few slides. So these giant ground-based telescopes that we're in the process of building are really going to change the game. They're going to image smaller planets than we can today, and we're going to spectroscopically characterize them. And a lot of us think that these ELTs should be able to probe the HAB zones of nearby M dwarfs. And as I was saying, that we've reached this point where technology isn't in the way, it's really just photon noise, and that lets us do some analyses about what the limits are for these telescopes and what the ultimate contrasts they're going to reach are. And this is by Olivier Guillaume. This is for the TMT working in H-band on an 8th magnitude star. And this blue line is the final contrast curve that he's predicting. And all the way in here to about 10 milliarcseconds, he's predicting 10 to the minus 8 contrast. A few years ago, Bruce McIntosh and company did a design and a simulation of a similar instrument working on the TMT. And they also came up with about 10 to the minus 8 contrast. And Marcus Casper at ESO has been working on an EELT instrument called the Planetary Camera Spectrograph, PCS. And this is PowerPointy, but it's based on a lot of simulation and analysis work by Marcus and company. And again, you see this number 10 to the minus 8, maybe getting down to 10 to the minus 9-ish as you get out to 100 milliarcseconds. And so to describe what kind of planets we'll look at with these instruments and what kind of science we'll be doing, I'll use this classic diagram by Olivier, where on the left you have contrast, on the right you have separation, and then you have these dots, each one corresponding to a star within 30 parsecs, color-coded by spectral type. So the blues are G stars, and then green, K stars, and then you're getting into the M dwarfs here, all these red dots. And the circles are telling you how close these stars are. And I'll start out by putting on a sort of very rough contrast curve for a space telescope. And there's that 10 to the minus 10 number that Carl was talking about. And because of that rule of thumb that you can always build bigger telescopes on the ground than you can in space, you'll see that the inner working angle of a space telescope is going to be limited by its diameter. And so this is the log of separation. So this is sort of, I would say, 50 milliarcseconds in here. And you can see this space telescope that can get to 10 to the minus 10 is going to look at sun-like stars. So these are G and K stars, and get down to 1 Earth radius planets in the habitable zone. I should stipulate that these are contrasts of 1 Earth radius planets in the hab zone that's plotted over here. Whereas with the ELTs, if you believe those simulations by all those different people that are coming up with about 10 to the minus 8 at the inner working angle and maybe getting down to 10 to the minus 9, ELTs are going to carve out this sort of contrast space where we'll actually be able to look at possibly Earth-like planets orbiting M stars within 30 parsecs. And so as Carl said, these planets are fainter, but remember that since we're in the hab zone, which goes as the square root of luminosity, as we move to these fainter stars, the planets themselves get closer, which means they get brighter. So even though these are faint stars, these planets are brighter than these planets. We also have the bigger diameter telescope, so we're getting more light. And most importantly, we have the better inner working angle because of the large diameter on the ground. So a key message here, though, is that the ground and space telescopes are not competing with each other for these targets. They each have their own niche where they're able to work taking advantage of their individual strengths. And so this is a key science project for these ELT instruments, and you don't have to think about whether or not we could do it from space or whether space is going to do it better. We're really in a complementary regime. So in conclusion, we have built and are building large telescopes on the ground from 5 to 10 meters now and soon to be 25 to 40 meters. Our big challenge is dealing with atmospheric turbulence, but we know how to solve this problem. Adaptive optics is now in routine use on all of these large telescopes. Post-AO ground exoplanet imagers are really similar to space-based. It's very similar technologies, coronagraphy, wavefront control, and post-processing. All these problems that apply to space exoplanet imaging apply to the ground. And again, I want to say ground and space are not really in competition. It's not a do one or the other or either or which one's best. We need both kinds of telescopes. We need to do exoplanet imaging both on the ground and in space.